Hello, everybody. Welcome to today's live stream on how AI confidence helps build better detection models. So, I'm Dan, I'm going to be your host today, and joining me is going to be Roger. So, Roger is our lead ML engineer here at Pictera. So, Roger, hello there. Can you tell us a bit about
Hi.
yourself, what we're going to be
Y-
covering today?
Yeah, hi, I'm Roger. As Dan said, I'm the lead ML engineer here at Patera. And today we're going to be talking about the concept of confidence. And I don't mean like the personality trait or anything. I mean confidence in terms of machine learning.
I'm in the wrong place. See you later.
Exactly. Uh, so yeah, I mean, I guess if we go to the next slide, we can dive right into what the concept of confidence itself means.
Sure. And I promise I'll make no more cheesy jokes. I'm sorry. So, yeah, let's start with the basics, Roger. Let's go all the way back and tell us, what is confidence in the context of AI and machine learning? What are we talking about?
Yeah, so especially with perception, so that is when a machine learning model is trying to learn to identify, say, an object or classify something. Um, there's a concept of how sure the model is of that detection. So I mean, in the end of the day, you can kind of think of your machine learning model as like a tiny brain, right? And it's not going to always be, it's not so black and white that it's 100% sure that it's detecting, that this is a cat and this is a dog, right? It's
Mm,
even though it shows the box around the cat and the dog, there is underneath that still some kind of like, well, is this really? I'm not entirely sure. A lot of machine learning models they'll define some kind of like predefined threshold and be like, okay, well, if it's over 50%, let's just call it that, right?
mm,
And then oftentimes you just won't even see what the actual what the actual sureness of the model is. But this is actually a pretty important concept, right? Because you know if it's at 51%, you probably want to know that, right? That's probably important information for you to sort of gain an understanding of how well your model performing and where are its weak points, where can you add more data, um, or also possibly maybe some data is mislabeled, maybe some in some places, so some dogs are labeled as cats and that's what's confusing your model. So it's important to understand how sure your model is of something in order to debug it, let's say.
okay, cool. Good to know. And we're coming from the kind of context of Pictera. So we both work at Pictera. We provide a platform that enables you to build models to detect objects, to detect patterns, to detect change in all sorts of different types of geospatial imagery. So satellite imagery, drone, or a type of top-down imagery. So, in the example that we see here, how is Pictera as a platform making use of this concept of confidence?
Right. So yeah, Pictera. I mean, I'm not sure how many of you guys have used the platform before, but basically you train a model and then you run detections, and then you can see here in green all the different detections of the planes here. And so the new feature we added is to allow you to sort of not see just the detections, but also the confidence values from 0 to 1 over these detections. So from a UI or usability perspective, basically when you run your detector on your imagery, you get these results. And the right hand panel, you see the layers there. You can click that little button on the looks like a little table next to the aircrafts. If you click on that button, you can view all the different attributes that are on your detections. In this case, the attribute we have here is the confidence map attribute. Um, and you'll be able to basically visualize the confidence on a color scale. So here, throughout all the detections, we found that the confidence values range from somewhere between zero point 0.8 and 1.0. You'll find that this is typical from use case to use case. The values have like sort of different ranges, but we decided it's still more important to sort of have a good visualization of the overall range of your values. So yeah, the lowest value is going to be set to like a black color, and then the highest value will be set to the color of the actual class color. So in this case, the green of the aircrafts. And so doing this can kind of quickly at scale in your imagery, sort of see the like spread of where things are lower confidence versus higher confidence. Um, yeah.
And this is quite a simple example of the aircraft that we can see. It's an RGB image, um, but in this example, well, it's a bit more complex. It's water bodies on a mining site, and it's using multispectral imagery. So what's happening in this example with the confidence?
Yeah, so this is actually an interesting example. You can see here, looking at the actual like water bodies here, you can see that there's some of the detections are actually not on water bodies. They're the black ones there are they're they're mistakes. And in this satellite imagery, things are a bit more blurry, a bit lower resolution. So this is actually a good use case of confidence because with this kind of like lower resolution imagery, well, compared to drones, you have a higher chance of things being uncertain because you just don't have as much pixel data as you do. So I think this is a pretty good use case. It's also cool because you can actually um, not only see like roughly where things are low confidence, but you can also look at the individual confidence values if you just click on say one of the black water bodies, and you'll see that like some of them have lower values. So this one, I think we clicked on a high confidence value here in this case, but we'll go through another example later where we'll see in more detail how to actually use sort of the like individual confidence values in the future slide.
What kind of confidence would that black water body have then in this example, as opposed to the ones that are
Mhm.
more vivid?
Yeah, so it is hard to define exactly like what numerical value it will have. Here, the confidence, as you can see, they range from zero point 0.8 to 1.0. You can see that kind of in like the slider on the right hand side.
Mm.
So the black ones here would have probably a value around zero point 0.8.
So it's still
It's
pretty
kind,
confident, but it's a relative scale between the
yeah.
minimum
I
and
mean,
maximum.
in the end, the detector still outputted it, right? So
Mm.
it's still like somewhat confident, even if it's wrong, that it is a water body. But we know it's not, so we wanted to highlight the fact that it's making a mistake there, which is why we decided to make even a high-ish level of confidence of zero point 0.8 into like the black color, just so you can really like focus on it and figure out why. But yeah, it's pretty rare that you'll get anything below 0.5, right? Because if it's below zero point 0.5, the model probably would not have outputted it in the first place. Um, so
Okay, gotcha.
yeah.
And then moving on, we're looking at some nice sea lions now on this. So, from a technical standpoint, kind of behind the scenes,
Mhm.
how is this achieved? What's actually going on to create these figures?
Right. Yeah. So we just talked a lot about the UI. So moving a bit more into the machine learning aspect of it, I think you've seen sort of these. If you've been to like looked at our docs or anything, you've seen these uncertainty maps. So these are available when you train your detector, so not on the results as we were showing you before. But in your accuracy areas, once you train a detector, you get these uncertainty maps. And so you can see kind of uncertainty and confidence are sort of the opposites, right? So in this map here, you'll see in the yellow spots, the brighter spots, where your model is uncertain. And you'll see a lot of outlines because basically for every detection that your model makes, the edges, which is where you are actually like what the model's trying to figure out, is this still in the object or outside the object? There's always going to be uncertainty there.
Mm.
So that's why all the edges are outlined in bright yellow. But then you'll also see a few like blobs here and there, like kind of denser yellow regions, and those are the cool parts to look at because that's where your model is actually like uncertain about the object itself and not just the edge.
So
So this
around
is
here, no? So kind of
exactly,
on the edge of this the flipper
yeah.
of the
So
sea
like
lions.
the fin is a bit like maybe I don't know. It looks like a shadow or a rock or something. I mean, who knows? The model
Yeah.
is doing its own thing there, right? So we actually use a concept very similar to this to actually derive the confidence values. It's not exactly the same thing, but it's kind of roughly using the same principle of yeah, to talk if you have a bit of ML knowledge about entropy and logits and all that. Um, but basically, what we do is that we take something similar to this map. We sort of ignore the edges because we know that every single detection has these uncertain edges, and we take the more important, like dense blobs. We calculate sort of the like average value for each blob, which is yeah, I mean it's basically just the like an inset version from the actual detection, And then from that, that's your uncertainty value, but then you just do one minus that, right? And you get the confidence because those are the opposite things. So that's kind of, yeah, underneath the hood what we're doing. The reason that we're doing it this way, so there are some machine learning models that will just directly output a probability,
Mhm.
but we're actually using a segmentation model underneath the hood for everything. So we have to calculate probability and confidence in a slightly different way. Um, so I guess the question now is like, how do we know that this technique actually works? Compared to some of the like, industry standards of using the direct output. And so
And
we
I have no
actually,
idea what's going on in this this graph on the right. So if you
yeah,
wouldn't
yeah.
mind explaining this a little bit, please.
I'll do my best. So we did a lot of internal tests to make sure that our approach actually works well. Yeah, we have a bunch of data sets, and we a lot of them, they're all labeled, so we know when the model detects something, whether or not the detection is wrong or correct already. So you can think of it as like data sets where we already have like a bunch of accuracy areas. And so what we did here was we basically like split out all detections that we knew were correct, and from all detections that we knew were wrong. And then for those two groups, we basically got all of the confidence values, and then plotted them or plotted their distribution to see how they compared. And the important thing is that like you want all the correct detections to have very high confidence values, right? And then you want all the wrong detections to have lower confidence values. Because if you have that split, then you know it's doing the correct job, right? All the wrong ones have lower values, all the right ones have higher values. Um, the ideal scenario, of course, is that like every single wrong detection has a lower value than every single right detection. In practice, I mean, if that were true, the model would have just output the right thing in the first place, right? It's always a little bit blurry with machine learning models. So the important thing here is more that the overall distributions look like they're skewed in a way such that maybe there's still some overlap, but in general, the wrong detection should have lower confidence values. And so you can see here that like most of our plots basically look like this for all like the different data sets that we tested, and you can see for the most part that indeed the true positives have a higher confidence value. The like average is the bright green, I think, whatever color that is, line in the middle of the box plots, and yeah, you see there's quite a difference there. And
Okay,
so yeah, what that
orange line to me. Yeah,
orange lines, yeah,
yeah.
colorblind here. So what that means is that like if you were to say like I don't know, like let's get rid of, and in this example, every single detection with a confidence value under I don't know, like point 0.8, right?
Hmm.
Um, so what happens there is that okay, yeah, there's some like kind of outlier like true positive detections there that you're getting rid of. So that means that your recall is going down a bit, but you're also getting rid of like more than half of the false positives. So your precision is going up by a lot, which means overall your score is your detector's performance score is increasing. So using this kind of knowledge can kind of like do a bit of like balancing between sort of the precision and recall of your detector.
Okay,
So
awesome. So
yeah.
so we know it works. So we're certain that it works, or pretty certain that it works. Um, Coming back to the title of today's session, we're talking about how confidence can help us build better models.
Mm.
So how does this work? I mean, how does it translate from everything you said to actually helping us to build a better model?
Yeah, so let's go through a specific example here. So here we have an example of like it's a bunch of palm tree, like a palm tree farm, basically. And it's a bit cluttered on the right hand side. Basically, these are a bunch of detections of palm trees. We kind of zoomed out a lot and like did the whole. We viewed sort of the markers of the detections, so you can just kind of see them when you're zoomed out.
Mm.
But we can actually color the markers themselves by the confidence values. And so, as I said before, brighter means more confident, darker means less confident. And what you can see here is that, like, on the left hand side of the image, for the most part, everything is quite bright and green, so things are pretty good there.
Mm.
And if you look at the zoomed in image on the left hand side, you'll see like, okay, these are all like palm trees, properly palm trees, and they're well detected, so it makes sense. I mean, they're pretty distinct. There's not not that much complexity in the background. So yeah, the detector is doing fine there. Good confidence values.
Okay.
But what's going on the right hand side there? There's like some darker values. So if we zoom in there, we'll see. Oh, this is actually over water, and that's why you get this like kind of like this. There are some green confident values. As I said before, there's a bit of overlap between the some false positives will still have good values, but on average, yeah, the values are much worse there. And so if you zoom in even more on the left hand side there, you'll see that like, oh, like sometimes there are these like little tiny black specks where it's being like falsely detected. So with this knowledge that we've gained from visualizing all the like the confidence values, um, what can we do to improve our results? So
Mm-hmm.
a few things. Well, first of all, the little tiny black specks, they're pretty small. They're small in a tree, right? So use a size filter, get rid of them. Um, I mean, maybe you could have determined that on your own without the confidence values, but the confidence value helped us find that problematic detection. So filter all those out. You'll already get a pretty good improvement in your precision. Um, the other thing you can do is if you go back one slide, actually, um, you can see. Yeah, I mean, we now know that this whole right hand side is water, right? And like we don't need to detect palm trees in the water. So draw a detection area over the land region and make sure you're only detecting there. And then you immediately eliminate all these like low confidence results over there. So like these are pretty simple fixes, right? But they have a pretty big impact on your results. And it's this confidence feature that helped us find them. Um, the other thing you could do to actually fix your detector itself is you realize, oh, hey, like there's bad detections of the water. Did I not add, training data there to make sure the detector knows to not predict stuff over water? And in fact, in this example, yeah, we only had training areas over the ground and not the water at all. We just kind of completely ignored it. So the detector basically had no idea what to do about water and sort of outputting the sort of random-ish results. Um, I'm sure like if you just added one empty training area over the water just to tell it like don't predict in this type of landscape, it would fix that pretty immediately.
Mm-hmm. Okay, awesome. So these confidence features are available today on the Picterra platform, but we're not stopping there, right? So there are a few things that we can kind of do next to
Mhm.
iterate ourselves on making these even more useful.
Yeah, so I mean, I talked a lot about how you can sort of gain intuition about the weaknesses of your detector and whatnot.
Mm,
One missing element currently is actually how to filter your detections themselves by confidence. So right now, all you can do is like visualize the results, but there's nothing in the platform that allows you to actually remove at scale, like in mass, everything below a certain value. And that's kind of the natural extension of this feature, right? But we are kind of working on the actual UI aspect of this to see how, like, what's the best way to sort of get an overview of your values. Maybe it involves something like exposing that like box plot. Is that too complicated for users to understand? So there's a lot of different UI considerations we're going through to figure out how to do that. The other cool thing actually is that this is a important to mention. This confidence feature is actually implemented as just an attribute on your detections.
mhm,
There can be lots of different attributes on your detections. You can have a height attribute. You can have an area attribute. There's a lot of use cases of the UI that we showed you earlier with the whole slider and all that. So it applies to every single attribute on your polygon. And so we also want to make sure that if we implement something, that it also applies to all types of attributes that could be on your polygons to make it sort of a really powerful tool, not just limited to confidence. The other thing that we're working on is better handling of segmentation mode. And so a lot of examples I showed you were kind of confidence over like smaller blobs, smaller detections, I guess you can say,
mm,
over the palm trees or over the airplanes. And it's pretty easy to calculate the confidence value there, right? Because it's a pretty defined shape of detection. You find the uncertainty in that detection. You do all that averaging stuff I told you about earlier, and there's your value.
mm,
Um, but what about for like, say, like a a result in the segmentation, like a land use result that covers, I don't know, like half your raster, right? It's like you would get just a single confidence value for that entire detection, which is not super helpful because in reality, maybe there's like one part of that detection that has higher or lower confidence than another part, and you want to focus on that area.
Mm.
But then if you want to split that out, then we have to like divide your detection into like sub detections and figure out how to like visualize that. But then we're splitting up your detection, which is maybe not what you want from a segmentation use case. Or maybe it's better just to show like the heat map of the uncertainty, and from that, that's already good enough. So there's also some like, yeah, I like to say that like ML a lot of the times is UI, but especially from like an engineering perspective, you can have like a really fancy model and whatnot, a really cool architecture that's cutting edge, but in the end, if you don't make it usable to users, then there's like no point in having it in the first place, right? So
Yeah, for
um,
sure.
yeah, so a lot of like both of these two things are sort of limited by our UX brainstorming right now. So we need to make sure we get it right first in terms of the experience before we actually put those things on the platform.
Okay, awesome. Well, thank you, Roger. I hope that's helped everyone kind of understand a bit more about how confidence and the implementation in platforms like Pictera, for example, really helps you build better detection models where you're detecting objects, change patterns within that geospatial imagery. So we're going to throw it over now to you guys. We're going to open the floor for any questions. So please feel free to give us your comments, your observations. Feel free to ask anything you like about confidence in machine learning whilst we have our resident expert online. And we'll take questions now. Thank you. All right. So as a reminder, you can take questions via YouTube, via Facebook, via LinkedIn, or via X. So we're actually live streaming across 4 platforms today. So let me check to see what we have coming in now. Okay, great. So actually, someone Roger has mentioned and picked up on the attributes. So they're asking, are there any other attributes besides confidence that are going to be added to the platform? Oops, I've just lost Roger. 1 second. Hopefully he comes back. There he is.
Sorry about that. My browser just crashed.
Okay, inopportune time. But did you hear the question? So the question was around attributes. Are there any attributes besides confidence that are going to be added?
Yep. The primary one that's easy for us to calculate is area. So that will probably be one that comes up soon. There's also like other geometric things like perimeter and whatnot that we could add. It's hard to know whether or not that's actually useful for people, so we're a bit unsure on that one. I think another big one is also just like the imported attributes that are already in the like you can upload your own vector layers into the platform. So we also need to want to support the attributes that are already there. Um, Otherwise, yeah, I mean, I'm sure there's other like machine learning based ones that we could add. Just we don't really have any good ideas for that one yet. So yeah, I mean, if you guys have ideas, then feel free to throw them our way.
Yeah, we're all ears. Do get in contact with us. Contact@pictera.ch. So let me see what we've got. We've got one coming in from LinkedIn. So how does your approach to confidence compare to, well, the more type that we saw in the first slide? So we had that cute dog and cat in the first slide, where the model outputs the confidence directly. How does the approach here differ?
Yeah, so we actually yeah, so as I said, like the cats and dogs approach with the box, the model directly outputs a confidence value versus our approach. We're actually taking the results of the model and then uh, basically doing some post processing to compute it after the fact. Um, we were actually initially a bit uncertain that this would produce good results, which is why we did all those internal tests to make sure that it was still working well.
Mm.
But actually, we compared against. So I think the model was YOLO. If you guys have heard of that, it's an object detection model, which outputs that confidence directly. And we basically did the same box plot tests with that model versus our model, and we found that the distribution of the points was pretty much the or distribution of the confidence values was pretty much the same. So, I mean, it's producing. And the other thing is that that's only on the data sets where the YOLO model would actually produce good output. So there's actually a reason why we use our model instead of the like object detection models. It's because our model works a lot better on smaller amounts of data, and since our platform is all about building your own model from scratch, that works a lot better than YOLO, which tends to require like a larger like data set in order for it to get good results. So what I just said about the results being comparable was only for the data sets where YOLO happened to produce like reasonable results. But for a lot of our other tests, YOLO just kind of failed to get good results in the first place. So it wasn't even comparable, uh, even from the get go. Um, so yeah, pretty confident that our approach is good.
Awesome. Thank you, Roger. Just checking to see anything else is coming in now. So again, a reminder, if you're on YouTube, if you're joining us from Facebook, LinkedIn, or indeed X, formerly Twitter, then please do pop a comment in. Give it a couple more seconds before we close up for today. No, well, as mentioned, sorry, what were you going to say?
I do remember that we forgot to talk about something.
Oh,
Yeah, I can briefly go. So I said earlier that we're going to talk about like how you can look at an individual confidence value to debug your detector, which I now remember I completely forgot to talk about. Um, so yeah, the water example was a good one, right? Because there were some bright green like detections in the water itself,
mm,
um, and so that's like a good indication that your model is not necessarily using the characteristics of like the palm trees, I think they were, that you as a human would look for in like detecting a palm tree, right?
mm,
It's still thinking like, okay, there's something about this thing in the water that has like certain features that makes me really confident that it's what you're looking for. um, so that's why it's bright green. But it in reality, that means that it's that the detector is missing the usage of some other characteristics of those palm trees to determine whether or not something is or isn't a palm tree, and that's why it's still detecting something in the water. um, at the end of the day, it's the solution is still the same thing, right? Draw a training area over your water, and therefore your model learns, okay, actually these characteristics are not what we want. Let's focus on different characteristics, hopefully ones that are more palm tree like, to figure out what your palm trees actually are. So solution is still the same as what I said before, but now you have a bit of insight into how your detector is actually thinking behind the scenes.
hmm hmm Okay, awesome. Thanks for the extra bit. So I don't think we have any more questions from the look of it. So all that remains, Roger, big thanks to you for sharing your knowledge with us this afternoon. Anyone has any further questions, don't hesitate to get in contact with us via the various social channels that we have, wherever you're watching us from today, or indeed drop us an email, contact@picdata.ch. But otherwise, thanks so much, Roger. Thanks to everyone for attending, and we will see you
Thanks.
all on the next GeoAI Bytes. Bye for now.